Here we're going to talk about power. Everybody watching this video has an idea about what the idea and concept of power is, right? What you need to kind of associate with power really, I think, is the unit, and then you'll start to understand. The unit of power is a watt, right? So we've all heard of watts. When you get a light bulb and it's 60 watts, that's a unit of power. Whenever you get a 120 watt light bulb, that means that that light bulb consumes more power, so it's brighter, right? So the higher the wattage or the higher the number of watts that something is producing or absorbing, depending on what you're talking about, there's more power involved, right? Power is the thing that gets the work done, right? It's what's actually doing work. In fact, when you look at the unit of watt, it's actually, and I'll talk about this and write it down in a second, the unit of a watt is a joule per second. So if you think back to physics, we learned about the unit of energy. Energy is joules, right? So energy is joules. That's how much energy is used or whatever in a process. But when you're talking about power, you're talking about continuous usage of this energy. So it's joule per second. So it's how many joules is being used every second. So in a light bulb, for instance, that's 60 watts, that just means that 60 joules every second going through that light bulb. So anytime you're talking about watts, you're talking about something happening continuously until you turn the thing off. So when you flip the light switch on, if it's 60 watts, it's 60 joules per second being, really irradiated, or so to speak, absorbed by that light bulb from the electricity coming from the wall, right? And being transmitted into light, but that's 60 joules every single second. So when you're thinking about power, think about that fact that it's every second something's going on. That's what the unit is. People get confused about the unit of joule, which is energy, and the unit of power, which is watt. Power, is something that's constantly going on. It's a usage of energy per second. All right, so in this lesson, we're going to apply these ideas to circuit elements. And so when we have a circuit, we're generally going to care. We're going to want to know how many watts something is using, right? Because we all have an idea that power usage is important in circuits. So before we get into a real circuit, let me draw sort of like a pretend circuit element up here. I'm going to draw a square. This could be a resistor in here. It could be, whatever. It could be 10 resistors in here. But I'm not going to care really what's in here, so I'm just going to draw a box because the concept is more important at this point. And connected to this box are, the wires that we always have in these circuits. So here's a lead coming out here, here's a lead coming out here. Now let me do some labeling really quickly. What we're going to say is the current flowing through this device is going this direction, and the current is value I. And across the box, across the device, we have a voltage drop. We're going to call it V. Now this should not be new at all to you, because we've talked about, when we have, just pretend it's a resistor here, we talked about the fact that when a circuit is going, you've got current flowing through everything, but the only way this current can actually flow is when you have voltage, right? So the source over here, which could be the voltage source pushing this current, is not shown in here. This is not a complete circuit. I'm just trying to focus on the power absorbed by this little circuit element, so I'm not drawing the rest of the circuit right now. It's kind of irrelevant. All we know, though, is by using a meter that we have so many amps of current flowing through the device, and correspondingly, we have a certain voltage drop across the device. And if you think about it, the V and the I, the voltage and the current, that's going through this device, are related by Ohm's law, because V is equal to I times R. Now we have no idea what's in here, so we don't know what the resistance is. That doesn't matter, right? When we know the voltage across something, the voltage drop, remember, voltage is always in terms of a drop. It's a sort of like we talked about this earlier. When you measure and you talk about a voltage, it's always going to be between 2 points. This part is higher than this part by a certain number of volts. We talked about that extensively before. When we know the voltage drop across a device and we know the current flowing through the device, then we automatically know the power that's being absorbed by this device. And so the power in this case, P, is equal to I times V. This is just as important as Ohm's law, so I want you to memorize this. P is equal to IV. This is your master power formula. This will always apply. Later on, we're going to find out that there are other ways to write power for resistors or even later for capacitors and inductors and things like that. But those things are great and they're simplifying. But this one is sort of like the granddaddy. It's always true. If you know the if you know the current that goes through something, and you also know the voltage across that same device, then you always know how much power is being, in this case, absorbed, because we're saying that this is like a resistor in here, right? So maybe it's absorbing 10 watts, right? What do you think, by the way, 10 watts is going to do? If we know that this box is absorbing 10 watts, where is that going? Well, usually it goes in the form of heat, right? So if you take a resistor and you stick current through it and you get a voltage, and you touch it with your finger, I'm not recommended, okay, but if you do, it's going to be hot, especially if it's generating, if it's not generating, if it's absorbing a lot of power. If it's absorbing 5 watts, then you're not going to maybe feel, depending on how large it is, maybe not so much, but if it's absorbing 100 watts, it'll burn your finger, right? So that's why a light bulb gets hot, because some of that power is going into heating up that light bulb, and some of that power is going into shooting light into the room. So that's what's happening in a light bulb too. There's kind of like a resistor in there that's heating up really when you look at the filament in a light bulb. So one thing that is so crucial to talk about here, 2 things really, is the unit. So let's talk about that real quick. We mentioned it. The unit of power is the watt. So when you take current, which is amps, and you multiply by volts, you get a new unit called watts. So I'm going to put that as a watt. And we abbreviate that just with a W, so if you have units here. And we also talk that a watt is a joule per second. So if you're in casual conversation with an engineer and you're telling them, hey, this is 50 watts of power, it's exactly the same thing as saying 50 joules per second of power, of energy flowing through that device, right? So 50 joules per second, 50 watts, same exact thing. They're synonyms for one another. All right, so we use this guy as the word watt because it's cumbersome to say joule per second all the time, and there's some history there. There's a person named Mr. Watt that did a lot of work with electric circuits also. Now, I want to stop here and kind of clue you into something super, super, super important, and that is the sign convention. We've talked a little bit about sign convention in the last section, but here it's very, very important. We're going to start to talk about the sign convention that you're going to use in all of the circuit analysis, beyond this point. All right, we know that when we have a current flowing through a device, and this device is a resistor or something like that, it's called a passive device. In other words, there's no voltage source inside there. There's no battery in here. There's nothing generating anything. That's what we call passive. This could be a resistor or a capacitor or an inductor or a transformer or anything else. As long as it's not generating anything, we call it passive, right? So active components, we'll talk about much later, those generate something. Those are sources and things like that. So if it's passive like this, right, which is what we're assuming, then when we have a current flowing through it, we should always expect a voltage drop like this, plus to negative, like this. And we've talked about that briefly before, but if it didn't sink in before, you really, really, really need to take a few minutes right now and sink it in now. Trust me, I've done all this stuff before. If you gloss over some of these things that I'm asking you to remember, then you're just going to make your life harder later on. So I'll say it 2 more times because it's so incredibly important. When you have a current flowing through a device, and it's a passive device, which is all of your resistors and everything else in a circuit, which is almost everything in a circuit, then you should always expect a voltage drop plus to minus in the direction of current flow. You can almost sort of like envision right here that this current is going from the plus to the minus, right? So if you take a voltmeter in a circuit and you measure the current and it's going this way, and you measure the voltage, you're always going to see it plus minus like this for passive components like resistors and stuff. So when you see it arranged like this, then you write your power with a positive sign. See, there's in front of the I, there's a positive here. And so when you calculate I, if it's 5 amps, times V, which is 10 volts or whatever, then you're going to get a number that's a positive number for the power. And when you get positive number for the power, this is the punchline. When you get a positive number for the power, when you calculate it, it means that that circuit element is absorbing that power. It means it's absorbing it, which means, think about your resistors. It's absorbing that power. They're getting hot. Think about your light bulbs. It's absorbing that power. Of course, it re-radiates that power as heat and light, but it's taking that power in from your source. So sort of the punchline is, when you analyze a circuit, you're going to be calculating power everywhere in the circuit. If you get positive numbers for your power, that means they're absorbing that power from the source. If you end up ever getting negative values of power in watts, it just means that that element is delivering power to the rest of the circuit. So later on, when we draw a complete circuit with a voltage source over here, what we're going to find is that this circuit element over here, which could be a resistor, has positive power greater than 0. That means it's absorbing power, right? Getting hot. The source over here, you calculate the power by that guy, and you're going to get a negative power, right? And that negative sign doesn't mean anything mystical. It just means that that element is delivering power to the rest of the circuit. So all of your sources should have negative watts, and everything else in the circuit should have positive watts. And the positive should equal to the negative because the source is delivering so many watts of power to that circuit, and the sum of everything else in that circuit, when you add it all up, should equal exactly what the source is delivering. Otherwise, it violates conservation of energy, right? So I've done a lot of talking, but it's so important for you to understand that because a lot of your problems are going to be calculate the power here, calculate the power here, there. Verify that the power absorbed is equal to the power delivered. If you don't know your sign convention, you're not going to be able to do it right because positive, negative completely determines how you interpret what this power is. It's just like sea level, right? When you have positive, 1,000 feet above sea level, you're above sea level. When you're negative 1,000 feet, you're below sea level, right? So it's the same thing in circuits. You have to have some kind of sign convention. Otherwise, you're just going to, you're not going to have a way to differentiate who's delivering the power and who's absorbing. So now that we've talked about that, let me show you what it looks like in the other case. Let me draw another box, same way. I'm going to try to keep the colors the same just for giggles. So this is a lead coming out here, this is a lead coming out there. All right, so in this case, I'm going to say we measure a voltage drop, just like in the previous circuit, it's exactly the same, but we hook our current leads up to the device. Let's say it's a black box, we have no idea what's in it. I mean, it could be a jackrabbit inside the box, could be hamsters running in a wheel. We have no idea. There's a box, right, and there's wires coming out, and that's all we know. So we measure a voltage, okay, we got that, and we try to measure the current. Now in this case, we measure the current, and the current is going this way. So we scratch our heads a little bit, and we say, that's a little weird. So the only difference between this one and this one is the current is going the opposite direction. You need to condition yourself, and I'm going to say this a few times because it's so important. You need to condition yourself. When you see a current flowing against the grain in a voltage, going from negative up to positive, then you need to recognize right away that that is not a passive component. All passive components behave like this, where you have the voltage drop and the current is going from the high, think at the top of a mountain. That's what I gave that analogy with voltage before. This is the top of the mountain. It's high voltage. That means high at the top of the potential energy curve, high at the top of a mountain. If you drop a ball from the top of a mountain, it's going to want to roll downhill. That's why the current wants to go this way for passive components, right? But here somehow we started at the bottom of the mountain with our current, and somehow the current went up the mountainside. That makes no sense. The only way that current can go from the bottom of the mountain voltage up to the top of the mountain is if I have a pump pumping that water or whatever it is up to the top of a mountain. So we don't have pumps in circuits. The only way this can happen is if it's a source, if it's a battery that's pushing that thing out with a chemical reaction, or if it's a wall socket that's pushing that current out from the power plant. Something active happening. That's the only way this can happen. This sign convention is so incredibly important because in a few sections we're going to write circuit equations where we're going to go around loops in a circuit and we're going to write down the voltage drops everywhere. So if you don't know the difference between these two cases, and you don't know how the sign's supposed to go, then you're going to just make it harder. It's going to be harder than it needs to be. So let me show you briefly in this case, when we have this guy, in this particular case here, we want to calculate the power that's sort of represented inside this box. What we need to do is put a negative sign like this, all right? We insert the negative sign because we recognize that the current is going against the grain. So the power has to be negative because remember, I already told you, negative power means a source. So that's all we're doing. We're being consistent with what I just told you. If it goes against the grain, there must be a source inside this box. So we have to put a negative sign there because negative power equals a source. So just to sort of drive it home, I'll draw a little conclusion box here. I'll do a little conclusion box here, and it'll just be really short and sweet. If you calculate the power of a circuit element, and you get a number that's greater than 0, that's a positive number, then what this means is that power is absorbed by the element. So think of your light bulb or your resistor. You should get positive powers there because it's getting hot. It's absorbing that power, which means it's absorbing energy every second, joules per second, joules per second. All right, now if, on the other hand, you calculate a power that's less than 0, then what this means is that power is delivered. Or you could also say supplied by the element, which really just means it has to be a source of some kind. It has to be a voltage source or a current source. It has to be a battery, or it has to be some power supply, or it has to be a wall socket, or it has to be something like that. All right, so in each case you're going to get watts. Here you might get positive 10 watts. Here you might get negative 15 watts. The sign tells you what the circuit element is doing. So let's nail this down to something real. It's, I think, a little easier to understand. Now that I've kind of gone through that, kind of like that overview, then you'll really be able to understand this no problem at all. So it's kind of worth the pain a little bit there. So let's say we have a 10-volt source. Very simple circuit. 5 ohms. And by the way, I want to tell you something right now. I'm drawing these incredibly simple circuits ahead of time in these early lessons here. And that's because most textbooks give you these concepts in a paragraph and then they throw you into these really complicated circuits. And usually students get lost. I mean, even I was lost at first because you don't know how to apply the concepts because they start out with such difficult circuits. So most of you guys looking at this, it's like it sometimes can seem extremely simple. Like, are we ever going to get to any harder problems? Well, you got to trust me a little bit here. I'm building your knowledge of these sign conventions and these really important things. In a couple of sections, I'm going to start going into some pretty complicated circuits that you're going to be able to handle because you have this foundation. So just be patient if you're looking at these examples thinking, well, these look a little too easy. So we're going to get there. All right, so we have a voltage source. Current is coming out of this voltage source. Notice that that's something we've always talked about before. When we have a voltage source, the current's coming out of the positive terminal and then goes around and around and around and around like that. So let's figure something out. We want to calculate the power. We want to calculate how much power is related in relation to that resistor, and we also want to talk about how much power is being delivered by the source. Now, since in this case we know this is a source and we know this is a resistor, we know that power is going to be absorbed here, and we know that power is going to be delivered from here because we already know. You see, over here I was drawing boxes on purpose, so you didn't really know what was in here. You can tell what's going on by the direction of the current flow and if you get positive or negative power. Here you know you should get a negative power for the source because it's supplying something. You should get a positive power greater than 0 for the resistor. So ahead of time when you look at your circuit, you should know what to expect sign-wise because you know the sign convention. So we know that the power of any element is equal to, in general, I times V, right? So we need the current to be able to do this, to be able to handle this. So we need to figure out the current here. Now, fortunately, you should think for a second, we know what the current is in this circuit because we know Ohm's law. We also know that V is equal to IR. That always holds as well. And since we know that this voltage here, this 10 volts, because of the wires here, it's connected physically across this resistor, the voltage across this resistor is 10 volts. So we know that we have 10 volts here. The current is what we're trying to find. The resistance is 5 ohms. So we can calculate the current. The current in this circuit, 10 divided by 5, is 2 amps. Now that's not what we want for the final answer, but we need that because the power is the current times the voltage. All right, so let's go and figure this out. Let's go and say, let's take a look at the resistor. Let's calculate the power for the resistor. So notice that we have the current coming down through the resistor like this. So we know from talking about the sign convention, and we talked about this earlier when we did Ohm's law as well, when you have current flowing through a passive component, you should always have, I'm going to write it in this circuit, but I'm not going to write it for forevermore. I'm just kind of getting your practice. The voltage across this resistor is something like this. Positive to negative. The current is flowing downhill from a high part of the mountain to the low part of the mountain. So the voltage polarity like this is positive, negative. When you look at circuits, you need to really start thinking about that right away before you calculate anything. If you see a current going through a resistor, positive, negative, it's flowing downhill. You need to think about that because the signs are going to be constantly coming up everywhere. So in this case, because the current is flowing downhill, so to speak, from positive to negative, then we use the first relation right here. P is equal to IV. The current is going from positive to negative, flowing downhill in the proper way for a passive component. So the power has a positive sign, simply because of the direction of the polarity. Now we know the voltage is this way from the same convention. So the power is equal to the current, which we just calculated, which was 2, times the voltage. The voltage comes from the source. It's physically connected across the resistor, so we know the voltage, this V here, is 10. So the power is 20 watts. And since it's a positive number, it's absorbed. Which means this resistor basically is getting hot. I mean, if you let it go long enough, 20 watts, that's a fair amount of power. It's going to get hot. And by the way, if you put too much power into a tiny little resistor, it'll just burn up. That's why the smoke comes out. You know, a professor of mine once told me that all electric components have magic smoke inside, right? And problems happen if you let the magic smoke come out, right? So that's what happens. So this resistor, if you put 20,000 watts in it, it's just not going to be able to handle it. It's going to burn up because the thing's going to get too hot, right? So let's go and look at the next component, which is our source. And let's see if this makes sense. So we want to calculate the power. So we say P is equal to, what do we think? Negative IV. Now there's two reasons you know it's negative. Number one, you know it's a source, so you know it's going to be negative. But I encourage you to look at the polarities because in more complicated circuits, it's not going to be clear unless you really follow the direction of the current and voltage to know what to do. This current is going around and coming up. This current is going from negative to positive. In other words, it's going against the grain. It's going from the bottom of the mountain up to the top of the mountain. And we already talked about that. Anytime a current goes from the bottom to the top of a mountain, the only way it can happen is if it's a source. So the power has got to be negative for this convention right here. So that's why we put a negative sign there. So negative, what is the current in this circuit? It's 2 amps. And when we get over here, through this particular element, it's 2 amps flowing through 10 volts. So it's 10 volts. So the power is equal to negative 20 watts. And because it's negative, it's supplied. Supplied to what? Well, it's supplied to everything else in the circuit. Now notice that you have 20 watts supplied by the source right here, which is negative, so that tells us it's supplied. And we have 20 watts radiated or absorbed by the only element that we have. So we have 20 watts supplied, 20 watts absorbed, which makes sense. You always have to have that in a circuit. However many watts is being supplied by your source must be absorbed by your circuit elements. Otherwise, you violate conservation of energy. So it always has to be that way. So I think that that's a pretty good example, very simple example, showing you how to interpret the signs and showing you that the passive components give you a positive power. The active component, which in this case is the source, doing some active production of current, is giving you a negative for the power. And the reason that the way that you differentiate between them purely has to do with this voltage polarity and how the current flows through them to help you choose your sign. Now, I hope that that's clear, but even if it's not, to be honest with you, we are going to do so many problems that you're going to, just be so comfortable with how that works. It's not going to be a big deal. So don't stress out too much if it's something that's not, right on the tip of your tongue, makes total sense. I hope it is. But we're going to do so many problems that you're not even going to have to think about that because you really have to be able to master it. And so we'll do it through examples. So to recap, in general, the power is equal to IV. Okay? Now, obviously, you can choose plus or negative, positive or negative sign here, depending on direction of the current, and if it tells you if it's a source or if it's a or if it's not a source. But in general, P is equal to IV. Now let me show you something else that's kind of cool. For resistors in specific, this also holds. P is equal to IV. It always holds. It holds for resistors. It holds for everything. However, we know that across a resistor from Ohm's law, V is equal to IR. This also holds. The voltage across a resistor is equal to the current through the resistor times its resistance, right? So what we can do is take this V and plug it into here. And when we do that, what we're going to get, P is equal to I times, we plug in this guy, I times R. So P is equal to I squared R. So this is true for resistors. This is another way to calculate power. Now, I'm going to come back to it in just a second. Let me derive something else, and we'll come back and talk about how this makes total sense. Let me show you. Let me draw a little squiggly line here to separate that, squiggly line there to separate that. Also for resistors, we have something else. P is equal to IV, obviously holds. We also know that V is equal to IR, holds. But notice if we do something else, if we solve for I here, Ohm's law, and solve it, we'll take V and we'll divide by R. All we did was solve for I. If we take this I and stick it back in here, we get a slightly different relation. P is equal to, we'll take this here, V over R times V, right here. So P is also equal to V squared over R for a resistor. You know it's for a resistor because you have a resistance involved in both of these cases. So why are we bringing this up? Because this is always true. If you know the current flowing through a resistor and you know the voltage across the resistor, then you always know the power. That's it. You just multiply them. Bam, you're done, right? However, depending on what you're doing in the circuit analysis, you may not really know the voltage across the resistor. You may know the value of the resistor, and you may know the current going through the resistor. Now, you can use Ohm's law to calculate the voltage, and then you can use that answer to find the power, but it's an extra step. So a lot of times, I guess what I'm trying to say, a lot of times in a circuit, you may know this is 5 ohms, right? And you may be given that this is 2 amps. Maybe you're not even given the voltage source. I don't know, I'm just making this up. On your test, you're given this, all right? So since you know the current through your resistor and you know your resistance, you can just use this to calculate the power, I squared R. So it means you would take, 2 times 2, because it's I squared, times 5. And that would give you a number in watts, right? Likewise, if you only know the voltage across your resistor, and you know the value of your resistance, you can square the voltage across the resistor, and you can divide by R. So a situation like that would be if I knew that this was 5 volts, and this was, 2 ohms. I don't even know what the current is in this circuit. I know the voltage across my resistor, right here, and I know the value of the resistance itself. So I can take 5 and square it, and I can divide by 2, and I'll get the power. So it's not anything different. It's not, they're all derived from this. So there's not anything new or fancy or crazy or anything like that. It just depends on what you have. It may be faster. In both of these cases, I know Ohm's law, so I can calculate the voltage here. I know Ohm's law here. I can calculate the current here. So in both cases, I can find I and V, and I could go up here and use this formula, but it's this exact same thing as using one of these relations here. Also notice that since it's I squared times R, no matter which direction your current's going, I squared is always positive. So, and R is always positive. So you're always going to get a positive value for power. That makes sense because resistors always absorb power. You're always going to get a positive number for power when you use these relations. V squared, doesn't matter if V is this way or this way. Doesn't matter if it's upside down because you're squaring the value of it, so you're always going to get a positive value for the power in a resistor, no matter what you do here. All right? So let's apply that to a couple of simple things, and then we'll wrap up this lesson and go from there. Let's say we have a very, very simple circuit, 8 volts. We'll put a resistor here and a resistor directly underneath it, and we'll say we have R1 is 2 ohms and R2 is 6 ohms. All right? Now what we want to do in this particular case is, for this problem, is we want to find the power absorbed by these resistors. Find the power absorbed by these resistors. Well, looking back to our lecture here, we need to have something. We need to know what the current is going through here, or we need to know the voltage across each one of these resistors. Now we know the total voltage across the whole thing, but that's not telling us what the voltage is across here and across here separately, right? So we need to find something. We need to at least find the current to be able to do one of these power calculations, right? Now there's lots of ways to proceed. I'm going to get a little bit ahead of myself because I think it's pretty easy to understand. When you have two resistors in a row like this, straight up, it's called in series. So this is 2 ohms and this is 6 ohms, you know? And so when you have them stuck end to end like that, we call it in series. We're going to talk a lot about this a little bit later for more complicated circuits. When you have that arrangement, it's exactly the same thing as adding these two resistors together. So really, if you wanted to rewrite an equivalent circuit, then what you would have is 8 volts connected to one resistor of a value of 8 ohms. These two circuits are really equivalent from the point of view of how much current is in the circuit. If you build this on a circuit board with 2 separate resistors and you measure the current, and then you build this one with 1 resistor and you measure the current, they're both going to have the same amount of current, because sort of something you haven't learned up until now, when you have 2 resistors in series, you just add them together. And so we're going to use that fact here, and we'll come back and have a whole lecture in this later on to kind of expand on it a little bit. But notice how when we simplified the circuit, now we can calculate the current very easily, because we know that V is equal to IR. And we know the voltage across this resistor is 8 volts. We're trying to find the current. We know the resistance. It obeys Ohm's law. So the current through the circuit is 1 amp. It's very easy to calculate that. I'll put a star by it because we're going to use it later. It's very easy to calculate the 1 amp here because of the simplification. It's difficult to visualize and to see how to do it here because you have 2 separate resistors. So combining them into one makes it much easier to apply Ohm's law. Now the true circuit that we built is this one. So what we've learned is that we have current. Here, I'll make it a little bit clearer for you. It's really going down there too, but it's coming up here as 1 amp. So it's going down and it's coming over. Now you see where we've landed. Because we know the current in the circuit, and we know the current through this resistor, and we know the current through this resistor because they're both in series. So the same current is going through both of them, right? 1 amp is going through here, 1 amp is going through here because they're daisy chained like this. So to calculate the power, we're going to use one of these relations we just derived. P is equal to, let's talk about the top resistor. P is equal to I squared R. All right, so for the top resistor, I is 1, so it's 1 squared times the value of the resistance, which is 2. So the power by the 2 ohm, I'm going to put 2 ohm resistor, 1 times 2 is 2 watts. All right, now let's calculate the power for the bottom resistor. P is equal to I squared R. Is equal to 1 squared, because that's the current, times the resistance, like this. So P for 6 ohm resistor is 1 times 6, which is 6 watts. Now, there's more than one way to solve a problem, all right? In this case, I used I squared R because I knew the current and I knew the resistance, right? But if I wanted to, I could use Ohm's law to calculate the voltage drop. V is equal to IR. I could calculate the voltage drop across here. And once I know this voltage drop, I could do V squared over R, the other relation for power that we learned. Remember, we learned 2 of them. V, if I know the voltage drop across a resistor, I can use this guy. Well, now that I know the current, then I can actually find that. In fact, it's a good little exercise. I'll just show you real quick. You all get the same answer either way. The voltage drop across this resistor is IR. It's Ohm's law. So the voltage drop is 1 amp times the resistance, which is 2 volts. So there's 2 volts. Here, I'll just draw it since we've kind of gotten to this point. There's 2 volts across this particular resistor right here. All right? And so if I calculate the power according to this guy, then I'm going to get 2 volts V squared over R, 2 squared over R. 2 squared, I should say R is 2. 2 squared is 4 over 2. So the power is 2 watts. the power is 2 watts for the 2 ohm resistor. You get the same answer either way, whether you use I squared R or V squared over R, or if you just use the regular granddaddy I times V, you get the same value of the power either way. I mean, it makes sense, you should. So in this case, I just use the current to find the voltage drop, and then I use the other relation to calculate that. So that was sort of like an aside. Now let's go back. We've calculated 2 watts through this resistor, 6 watts through this resistor that's being absorbed. How much power is being delivered by the source? You should come up with an answer right now without even doing any calculations. If I'm absorbing 2 plus 6 over here, I'm absorbing, or I should say I'm sucking in and converting to heat 8 watts, right? Through these resistors. So I should be delivering 8 watts from the source to balance everything out. So let's figure it out. So let me change colors, and we'll say for the source, P is equal to, we can't use I squared R, I mean there's no resistance here, we have to use IV, right? But we need to be careful about the sign. The current's coming down, going over, going up. The current is going against the grain. It's going from negative to positive. We've talked about that many times. When the current goes from negative to positive, we put a negative sign in. So even if you had no idea that this was a voltage source, you would be able to figure out that it should be negative IV simply because you have positive, negative, and you have a current going against the grain, like that. All right, so negative IV, which is equal to negative, the current is 1, the voltage is what? It's going through 8. So the current going through this device, 1 amp, 8 volts. So the power source is negative 8, unit is watts. 8 watts balances with 2 plus 6, which is 8 watts. And this means power is being delivered, and these positive numbers mean power is being absorbed. All right, that about does it for the lecture. I just want to point one more thing out to you since I already kind of went down this rabbit hole here. We found that the voltage drop across this resistor is 2 volts. Let's figure out, just for giggles, what the voltage drop is across these 2 resistors. So we know the current and we know the resistance. So we know that the voltage drop across anything is I times R, right? And so we know the current is 1, and we know the resistance of this bottom guy is 6. So the voltage drop across that bottom resistor is 6 volts. And since the current is going down through a passive component like this, we know that it looks like this, plus minus 6 volts. There's a couple things I just want to mention to you. Notice that you have 2 volts of a voltage drop across this component and 6 volts of a drop across this component. Notice 2 plus 6 is 8. That's the same voltage we started with. So we're going to, I just want you to sort of see that and say, oh, that makes sense. We're going to come back to that sort of point a whole lot more later on. This voltage drop exists across these 2 components. So the total of 8 volts must exist between these 2 endpoints. And you can see how it's split up. The 2 volts is across the smaller component and the 6 volts is across the larger component. It's all self-consistent. You don't need to solve for all that stuff unless your problem asks for it. But just notice that the sum of these voltage drops equals the sum of your source voltage. And that's what we have. So I want to do a quick summary because we have covered a lot. But it's very, very important material. So we talked about power. We basically said, look, if you have no idea what's inside of a box and you're just told that you have voltage drop like this and a current like this, then you automatically know that you have positive power. And positive power means power is absorbed, means something's getting hot because it is absorbing power from something else. If you have an arrangement like this where the current is going against the grain, uphill like this, then you must put a negative in your power calculations. That will lead to a negative answer for your power. Negative by sign convention means it's supplied power. Everything else to the circuit is being supplied by this guy. So when we have a simple arrangement like this, we can calculate the current, and when we know from Ohm's law, because Ohm's law is always valid, and then we calculate the power absorbed by the resistor, we calculate the power delivered by the source, and it's equal and opposite, and it always has to be like that. All right, so then we talked about, in general, IV is the power. But for resistors, because of Ohm's law, we can substitute in and find out that this is another relation for power, and this is also an equivalent relation for power. It just depends on what you have. If you know the voltage across something and you know the resistance, use this guy. If you know the current and the resistance, use this guy. If you don't know either one of those and you know this, use that guy. It's all the same thing. And then finally, we had a slightly more complicated circuit. I mean, it's not that complicated, but it's more complicated. We learned that series resistors can be added together. The only reason we did this is so we could calculate the current in this circuit. And once we knew that, we could calculate the power through this resistor, which was 2 watts, the power being absorbed by this resistor, 6 watts. That's 8 watts of power that's being absorbed by those components. When we take that current back around here, and apply it here, we put a negative sign because of the convention, and we also see that we have 8 watts of power being delivered. Power delivered equals power absorbed. And to be honest with you, that's probably the whole lesson here. Power delivered, power absorbed. It always has to work out that way. So it's kind of like a nice check on a test. If you're asked to do that kind of calculation, they really need to balance. If they don't balance power-wise, then you've done something wrong somewhere. And it very likely is a sign error somewhere. So check that out. Now again, I want to stress, all of these problems have been trivial from the point of view of the circuit, right? There's no branching going on. The current's not splitting anywhere. But I'm trying to get these fundamental ideas drilled into your head so that when you're looking at a circuit with 5 branches going everywhere, you have very comfortable understanding of sign convention and how it should look, so that whenever you're writing your circuit equations later on for more complicated problems, then it won't worry you so much. You'll have that confidence so that you'll know you're doing the right thing and you'll be on the right track for more complicated types of problems. Learn anything at mathandscience.com.